So we'd like to give names to some of these expressions that we've created so that we can use them time and time again in building up bigger expressions and actual programs. So we can give names to some of these things. Well, we can write let x equals 200. So the formulation there is the word let, followed by the name we want to give, followed by the equals sign, followed by the expression that we want to associate with that name, the expression whose result we want to associate with that name. So now we can write x times x times x, and that will evaluate to 200 times 200 times 200, which is 8 million. Okay, if we want to do this all in one expression, here we had two expressions. We had let x equals 200, and then we had x times x times x. This is how you might type it in to OCaml when you're using the interactive OCaml. But we'd like to combine these all into one thing, and to do that we use a slightly different formulation. We write let x equals 200 in x times x times x. So here we say let, the word let, the name we want, the expression whose value we want to associate with that name, then the word in, and then the expression which uses that name. And you can have more than one of these. You can write let y equals 2 in let z equals y times 4 in y plus z plus 1, for example. And looking at the types, well, this has type int, which means that because it's assigned to x, well, x must have type int now. So all these have type integer. We know that when we multiply them together, we get type integer 2. And so every expression in ML has a type. So what's the type of this whole expression? Well, that too is int. Well, this is slightly useful, but it's not very useful. To go one step further, we want to create functions which are expressions into which a value can be plugged to get a different result for which value you put in. So we could write a function let cube x equals x times x times x. Now here we've got slightly different syntax. We've got the word let, then we've got the name of the function, then we've got the name of the parameter, and then we've got the expression that results. So this is how to define a function. This function can take any integer you give it and cube it, giving you another integer. The first question is, how do we use that function? Well, we just put the value we want to give as the parameter next to it. So cube 200, the expression evaluates to, again, 8 million. But what are the types of these expressions? What's the type of cube? What's the type of cube 200? We know that the type of what goes in is integer, and we know the type of what comes out is integer 2. Well, to write the type of cube, we have, again, a new symbol. We say that cube has type int goes to int. We put an arrow and we'll pronounce that goes to. So cube is something of type int goes to int, which means you give it an integer, you get an integer out. So we can write that type here as well. Int goes to int. So the correct things happened. We took a function of type int goes to int, we fed it an int, and so what did we get out? We got an integer out. And we can give more than one thing to a function. Here's a function which is going to detect if two numbers you give it add up to 10. Let add to 10 ab equals a plus b is equal to 10. Well, what does this type have? What's the type of this function? Well, it's something where you give it two integers and it gives you back a boolean. True, they add up to 10, or false, they add up to something else. So in this case, this has type int goes to int goes to bool. So we have more than one arrow here because we have more than one parameter. So int, int, bool, int, int, bool. We can write those there. Int, int, and bool. And you can have 3 or 4 or 5 parameters depending how complicated your function is. As a final example, let's look at a recursive function. Now, recursive is a new word. A recursive function is just a function whose definition uses its own name. That'll become a bit more clear when we take an example. The factorial of a number, so 4 factorial, as we know, is equal to 4 times 3 times 2 times 1. Or more generally, n factorial is equal to n times n minus 1 times n minus 2 dot 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 1. How can we express that as a function? It's a simple enough function in theory. An integer comes in, an integer goes out, so it should have type int goes to int. Simple enough. So to define that function, again, even more new words. When a function uses its own definition to calculate something, we have to put the extra word rec in there. That just stands for recursive. So let recursive, we'll call our function fac. It takes a number n. Well, we're going to do n. In most cases, we want n times n minus 1 times n minus 2 and so on, but we have to know when to stop. So we better test for when to stop. So we'll say if n equals 1, then the answer is just 1, which is our base case. Otherwise, our answer is n times the factorial of n minus 1. So you can see here that in our expression, we're using ourselves. So how does that evaluate? Well, if we try and evaluate fac4, we get, well, n is not equal to 1, so we get 4 times fac3. Well, that now reduces. We get 4 times 3 times fac2, and again 4 times 3 times 2 times fac1. That is the base case. So we get 4 times 3 times 2 times 1, which in fact is what we want, which is 24. So that's called a recursive function. The only difference from a normal function is that because it uses itself, we need to put the let rec instead of let. But notice that its type is just as simple as before. The type tells us what comes in and what goes out. It doesn't tell us about what happens in between. That's the whole point of a function. So an integer comes in, an integer goes out.